So let's extend our study of circular motion to a couple different applications. And the first being gravity and how we have to take the rotation of the Earth into account. So suppose you're at the equator standing on a scale. So the Earth is spinning around. The weight that you read on here is not going to be your actual weight. It actually changes depending on the latitude. And so what we can do is we can think about circular motion and figure out exactly how much it's changing. So what I've done is I've redrawn this. So we're looking at it from this perspective. We're looking down on it as you spin around in a circle. So you stand on the scale. There's two forces acting on you. There is the force of gravity, which is centripetal in nature towards the center. But then you also have the normal force coming up. And that's the force of the scale. And remember that the normal force on a scale, that's your apparent weight. Apparent weight. And when you're at rest, so at rest, we know that the apparent weight is equal to your actual weight. So at rest, the normal is equal to the force of gravity. So we want to see what happens when you're actually moving in a circle. So since this is a circular motion, we have a net centripetal force, and that's going to be your mass times your centripetal acceleration. So the net force, we take in to be positive, so the force of gravity, and then the normal force is outward, so minus the normal force is equal to mass times, I'm going to leave it as AC right now. And then if we rearrange this, then we get the normal force is going to be the force of gravity minus the mass times AC. Okay, going back to review, remember that the centripetal acceleration is v squared over r or omega squared times r, either one of those. We're going to use this one. So the normal force, your apparent weight in this case, is going to be your actual weight minus the mass times the angular acceleration squared times the radius where you are. And so what we can see is that the normal force, the weight, has been reduced. And so let's label some of this stuff. This is your apparent weight. I misspelled that, apparent weight. This is your actual weight. And this quantity here, please don't get confused. This is what we refer to as I'm going to put it in quotes though, because it's not real. Okay, so let's talk about this. What this is dealing with is a non-inertial reference frame. So because this is constant circular motion, we have acceleration. And if we have an acceleration frame, what that means is the Earth, in fact, is non-inertial. And since it's non-inertial, we can't use Newton's laws of motion, but we really want to, and they all hold. And the way that we can account for it is by pretending that there is a force. So this is not a real force, but if we treat it as one, then everything works out. And so nothing changes. Now, this quantity, you might be wondering, how much does it actually change stuff? Not very much. So this quantity, the m omega squared r, that's going to be 0.033 meters per second squared at the equator. At the equator, and it gets less as you move away from the equator. So you'll have the greatest effect at the equator. So you weigh less at the equator. You weigh the least. There you go. The reason being, remember that the distance, the r that we're talking about, is the distance to the axis of rotation. So when you're standing here, your r is right here. So you can see we have less r than we do here. So we've reduced r which reduces this quantity. And if you go all the way up to the pole, you're spinning in a circle, but you're not rotating. And so this goes away. And so at the equator, you would have your full weight would read on the scale, and we would get this quantity here. Now, this does have an effect on the G, how we measure G, but it's nothing that we can't account for. So kind of knowing this, that as you move towards the equator, you weigh less and less. And as you move toward, and conversely, as you go towards the poles, you weigh more. Okay, centrifugal force, it's not real. All right, let's talk about loops. So loops. So think about going over a hill, and we want to think about why we feel like our stomach goes up. So let's just pretend we're on a magic chair that can go over a hill. So we're traveling and we're gonna go like that. So this is a circular motion. Okay, let's get the forces involved here. So we're gonna have a normal force and the force of gravity. And what we want to see is what's that normal force. So as we go over, this is circular motion. So we start with net centripetal force is mass times centripetal acceleration. The net force inward is positive, so this is Fg. And the normal will be negative, is mass times v squared over r. I'm going to use this definition now. Rearranging this, we get that the normal force is going to be Fg minus mv squared over r. So what we can see is that the normal force is reduced. It's similar to what we just did. In fact, I think it's the same picture. So we can see that the normal force gets reduced. And so there's a speed at which we would get so big that the normal force would be zero. And we would fly off of this thing and escape. But there you go. This should be familiar. The other case is when you go through a dip. So the sensation you feel when you go through a dip. And the analysis of it is the same. I'm just gonna do this. Okay, so we still have a normal force, but since we're going in a circle, we know we know this one doesn't change, this one's fixed. And since we have to have a net force up, this one has to be bigger, so we feel heavier. In this case, the normal has to be smaller because we have to have a net force down. So this net force has to be up. So again, we get the net centripetal force is equal to the mass times centripetal acceleration. If we take n to be positive, then we flip it. We have the normal minus the force of gravity is equal to MAC. I'm just going to leave it the AC. So we see that the normal is going to be the force of gravity plus mass times AC. So we can see that our normal force increases. So our apparent weight increases when we go through a dip, and that's what we feel. We feel a lot heavier when we dip down through it. All right, the last case I want to talk about is going under a loop like this. So you have a roller coaster on a track like that. One of the questions we might ask is like, how fast do you have to go so that you'll make it through the loop? And to do that, we're just it's the same type of analysis, except in this case, the normal force is in this direction. Let me switch to yellow. So the normal force is this way, because that's the force of the track on the car. So here's my normal and the force of gravity. I'm talking about, let me redraw it because somebody's going to complain. So normal force this way, force of gravity this way. Okay, so the net force here is centripetal in nature, and that's going to be mass times centripetal acceleration. Both of these are positive, so we have, because they're inward, so you have normal plus the force of gravity is equal to the mass times v squared over r. Now, what we wanted to know is what's the minimum speed that you can make it through the loop. So we have to think about what happens if you go below that speed. You know, if you go below the speed, if you're going too slow, eventually you're going to come off the track. And that means that the normal force is zero. So we want to know, when is the normal force going to become 0? And if we do that, then we can figure it out. So we're going to let this be 0. So we get mg is equal to m times v squared over r. And then my m's cancel, multiply the r and take the square root. We get that the v is going to be the root of gr. And so that is called critical speed. But the analysis is pretty quick. Yeah, and that's it. So this is just kind of, always set it up. You'll start with your Newton's second law for circular motion, and then just figure out your forces. Remember, inward is positive, outward is negative. You can use the tangential velocity or the angular. It just depends. But that'll be it.